Hey, welcome back to Fat Mom Physics. In this video, we are going to continue on with exponential decay and half-life. So in this last video, we have an idea of all the definitions. We got it, and we also were able to see how this equation is derived from the definition of the radioactive decay. Okay, so in this video, I'm going to do tutorial example 2, 3, and 4, which is playing around with this equation to do some of our bidding. Okay, so let's begin. We should get that. Yes, we did. Use this question to find an expression for half-life. I'll use this expression, probably. Anyways, the question's weird and funny. You should get half-life is equal to this. Okay, so essentially, we want to use this equation to give us an expression for half-life, where T is equal to half-life, okay? So, we're going to use that, okay? We also know for half-life is that the fraction between the number of parent nucleus to the original before the decay is exactly half, okay? So when we look at this equation over here, which is n equals to n naught e negative lambda t, okay, what we can do is if we divide both sides by n naught, okay, then we're going to get n over n naught, and hey, that's going to be a half for half-life, okay? For half-life, this ratio is going to be a half. This fraction is going to be a half, and this is going to be equal to whatever the other side is, e to the power of negative the decay constant, and the time, we're going to use this one for half-life. So t and subscript half is the half-life, the time of the half-life, okay? So what we're saying is that the half-life is going after t amount of time, which is the half-life. After the half-life has passed, then the initial amount of radioactive nuclei will half as well. Okay, so we're going to work this out to give us an expression for t a half. So working with this side of the expression, if we want to get t down off from the exponent, it's like, hey, get off your high horse. We got to take the natural ln of both sides, okay? So I'm going to take the natural ln of this side, and we're going to take the natural ln of this side, okay? So this level of math, you are required to be able to do at the HL level. If you don't know how to do the calculus, that's okay, but know how to work your logarithms. Okay, so after we take the log of both sides, we're going to end up with ln of 1/2. Did I say natural? Yeah, natural logarithms. This is going to be equal to ln of e to the power negative lambda t a half. Okay, so let's change this up a bit. So what we're going to do is, I can't have ln of a half. There's no ln of a half in here. So how do I get ln of 2? To get ln of 2, we know that 1/2 is essentially 2 to the power of negative 1. That's exactly the same thing as 1/2. To take the ln of e to the power negative lambda t half, remember, whenever we take the ln or the ln or the log of something, the exponent drops down in front. So we get negative lambda t a half of ln e. Okay, we know that ln e is equivalent to 1, so that actually just goes away. So if we continue doing this on the other side, in fact, let's drop the negative 1 in front as well for the ln 2. So we drop negative 1 in front, we're going to get negative ln of 2. Ooh, that's getting closer to what we want. This is equal to negative lambda t 1/2. And the nice thing here is that these two negatives are going to be able to cancel out. And we are left with ln 2 is equal to lambda t a half. So to isolate for t a half, which is the half-life, we're going to divide both sides by the lambda to do that. So rearranging for half-life t half here in front is going to give us ln of 2 over the decay constant lambda. So there we go. We have now shown that this is how we can figure out the half-life assuming that we have the decay constant. So if we have the decay constant, we can figure out half-life. If we have to know the half-life, we can figure out the decay constant. And that's very useful because we need the decay constant in order for us to use this equation so that we can figure out the number of nuclei at any point in time. So notice that this is a constant decay. It's not just a geometric series in which you have something that looks like this, and in which you have some starting amount of nucleus, radioactive nuclei, and then that halves for some amount of time. It doesn't quite work that way. This is this is looking at discrete data, but whenever we have radioactive decay, it is a continuous decay. Okay, so that's why we get that. Okay, here we have example 3, which is not too troublesome, because what we need to do is just show that this can also be expressed as that this other form using activity. We also know that activity is equivalent to the decay constant times the amount of radioactive nuclei at that time. So what we can do is we can rearrange this so we do get n on one side of the equation. And what that means is we're going to get n is equal to activity over lambda, okay? So let's plug activity over lambda in this equation. We're going to get activity over lambda is equal to n naught e to the power of negative lambda over t. So we just need to multiply the decay constant up to finish this off. So here, if we multiply the decay constant, we're going to have lambda times n naught, initial radioactive nuclei, e to the power of lambda t, which looks exactly what we see above. So that wasn't too bad, okay? The number 4 is going to be trickier, and number 4 is going to be very important because you are expected to know how to figure this out, okay? So here we have a graph of a function of natural ln of the number of radioactive nuclei versus time. What would the gradient, which is the slope, what does the slope mean, and what does the y-intercept mean? We should use this equation to help us out. Keep in mind we can produce a similar graph with activity A instead of N. So yes, that comes later on in example 6. We'll do later, okay? So let's do example 4 together. Okay, so if I graph the function, it looks like we should take the natural ln of both sides. So we have n is equal to n naught is e to the power of negative lambda times t. So let's take the natural ln of both sides of this equation. After we do that, we're going to have ln of n is equal to ln, and here we're going to have a big cluster of things inside. So okay, let me do one step at a time. So this is going to be n naught e to the power of negative lambda t. So keep in mind we can't drop the exponent yet, because technically this is n naught times e to the power of negative lambda t. So to separate the two, remember that if I have two powers that multiply, so for example, if I have x to the power 5 times x to the power 3, then I have to add the exponents, which is x to the power of 8. So it's just like for logs and natural logs, is if I have two things that are multiplied together, it's like me adding them up together, the natural logs together. So this is going to look like this, okay? It's going to be ln of n naught plus ln of e to the power of negative lambda t. So this can be simplified even more. Natural ln of n cannot be changed. And this is fine because we actually want that plotted in our y-axis. But we are left with ln of n naught. And don't forget, n naught is a constant. It's the amount of radioactive nuclei we start off with. And to take ln of e to the power of negative lambda t, I did show this earlier, but don't forget that if this is okay to drop the exponent in front, because that's the only that's the only power ln is applied to. So we have negative lambda t ln of e. And we know ln of e, this is just equal to 1, okay? So what this becomes is, it becomes, don't forget the negative sign, so it's negative lambda t, and that's it, because ln e is just equal to 1. So that is essentially the equation that we have. And what we want to do now is we want to compare this to y equals mx plus b, since that's essentially what we're trying to go for. So let me rewrite this here to show the comparison. So to write it again, I'm going to write ln of n. This is going to essentially be my y, okay? And what I'm going to do is, since the x-axis is time, I'm going to move this to the front to match up with the mx plus b format. So negative lambda t plus ln of the initial number of radioactive nucleus. So this is the same thing. And to compare this with y is equal to mx plus b, we now see that the b is just ln of n naught. And the m is just negative lambda, which is the time constant. So, hey, we just did it. This, where is it? The y-intercept here is essentially the non of the n naught, which is the original amount of radioactive nuclei, and the gradient here is going to be negative of the decay constant. And it makes sense because the slope is going down, so that justifies the negative sign, and the magnitude of the slope is going to be our decay constant lambda. Okay, so just by plotting your data, you can figure out the decay constant, and from the decay constant and the y-intercept, you should be able to predict the amount of radioactive nucleus after a certain amount of time. Okay, so there we go. All right, and that's it. We are going to stop there because the next few examples are actual calculation examples. But here we go. This is more of the theory stuff. Anyways, thank you for watching, and hopefully you learned something in this video. I wish you best of luck. Fat Mama Physics signing out.